Welcome back to ECE 441A 541A. Homework number 2 is not due on a Friday, it's due on a Wednesday. And it's not this Wednesday, it's a week from Wednesday, but then our exam will be the following Friday. I have made available exam number 1 material, and that's on D2L, and I've also made lab number 1 material available. That also is on D2L. I want you for the lab to form teams of 2 to 3 so that we don't have 70 different labs going on. We only maybe have 20. The lab itself is in room ECE 331, and I'll talk a little bit more about that maybe Wednesday, but I want you to be thinking about who you might team up with, and I'll possibly pass around a sign-up sheet so that you can sign up for your particular pieces of the lab. By that I mean you're going to have springs, and the spring that you'll identify, unless it's tagged, I think spring number 1 is the only one that's still tagged. The others actually have a engraved number on the end. So you'll have spring 1, 2, 3, or 4 that you will be playing with. I wanted to bring one in and maybe grab an apple from one of the students and put an apple on the spring to see what the spring constant is. But you will be determining that experimentally from your step response. And we'll just assume that you know what mass you have, where the masses are 500 grams and the cart itself is 500 grams. So if you have 2 masses assigned to you, you'll place those 2 masses on the cart. This will make more sense if you watch the demonstration video and look at the notes that are available on D2L. And you will also attach your particular spring, and then you will try to identify what the spring constant is, what the damping constant is, and from that you'll have your transfer function for a second order system. That's lab number 1. Today what I want to talk about is the situation that we had a quiz on last time, and that is, what do you do when you actually don't have a linear system? And sometimes you don't have a purely linear system, and a linear system or a nonlinear system is one that might have a product of terms, like a position and a velocity. Maybe those are multiplied together. Maybe you have the sign of one of your state variables or a cosine, but it has some nonlinear behavior or characteristic to it which violates these 2 properties that a linear system actually possesses. A linear system actually has 2 characteristic properties. It satisfies superposition or additivity and homogeneity. And these are really just a functional description of what we mean by superposition and homogeneity. Essentially, if you had the combination of 2 variables, you add those and you take their functional, or you put those in the argument of your function, then that's going to be equal to the sum of the individual functional expressions applied to x sub 1 and x sub 2 individually. Likewise with homogeneity, if you scale the input variable, that's the same or equivalent to scaling the result of the functional form. And I think we're all familiar with a linear function. You can think of it as some relationship between x and f of x, and if it's linear, that's what we like, or that's what we prefer. And that's what we will be analyzing or designing with. We will be assuming that our systems are linear. Some systems or common ways of finding nonlinearities: if you have an amplifier, or if you even have a resistor. Maybe if you drive it too hard or too far, maybe it's no longer directly proportional to the current. in terms of a resistor. Or an amplifier, maybe it saturates at a certain value or voltage. You might have a dead zone nonlinearity, which might be, it may take you a certain amount of voltage to get something moving or started. That's another nonlinearity. Or you might have, and I'm really going through this quickly, but I just want you to understand that there are nonlinearities, and then we'll figure out how to deal with those, and we'll slow down and we'll work through that process. Another nonlinearity is a backlash, where you might think of gears, and the gears may not engage until you get rid of that sort of gap between the two meshing gears. And then you try to turn around and go the other direction, then it doesn't really engage for a little bit of a distance, and that's what we mean by backlash or a backlash nonlinearity. As I said, we will be analyzing and designing based on our system being linear. We need to figure out, what do we do if we do have some nonlinearity in our system? And I think the answer is obvious, since that was the goal of this lecture. We want to be able to perform linearization, or we want to linearize the nonlinearity. Let's then look at that by means of an example. Suppose that somebody gives you the following, or you observe the following behavior. You look at the first derivative of a variable, let's say your state variable, and you compare that with 2x squared, and that's actually equal to the input maybe that you've applied to the system. We will typically write our dynamics such that the derivatives are on the left and everything else that drives it is on the right, meaning this system now could be written as the time rate of change of the state variable, x, is equal to 2 times that state variable squared plus the input u. And that particular right-hand side makes this whole dynamic system nonlinear because of that x squared term. Meaning you might just see this written as x prime is equal to f of x of t u of t, and without knowing what f actually is, it may be linear or nonlinear. The linear case is typically when we have this matrix A times x plus b u, where x is maybe a vector. Now f could be a vector. In this case, we're just assuming we have a scalar, and now the right-hand side does have a nonlinear term in it. It only takes one to make the whole thing nonlinear. And this now is a nonlinear dynamic equation, and what we want to do is figure out, can we play with this or adjust this such that it will become a linear system, maybe in some certain region. And a way to see that would be to just think of what you might have traditionally. Let's say here is x, and this is f of x, and maybe you see that your particular expression looks something like that. Now what you may want to do is you might say, well, I'm interested in operating my system at around that particular region, or in this case, that point in the state space domain. And what we would be doing then is we are now trying to find the tangent line, or we are trying to linearize that nonlinear expression, and nominally then it will have a value of x sub naught. So what we're trying to do is find, depending on where we are operating, we want to now find an approximation to this nonlinear behavior, and that's our goal, and that will then replace or approximate this nonlinear side on the right with a linear approximation. That's what we're wanting to do. Now, how can we formalize that? We go back and we look at some of our math techniques and we say, oh, a Taylor series allows us to start finding things in terms of linear term, an x squared term, an x cubed term. Maybe if we throw away all those higher terms, we can just approximate that nonlinear expression with the linear piece. And that's what we're going to do. If you remember the Taylor series, let's say that we now have f as a function of two variables, let's say x and u, where x is our state variable and u is our input variable. The Taylor series expansion says, oh, we find what it is at the nominal location, x0, u0, and then we start looking at how the system changes away from that particular location by performing partial derivatives and higher partial derivatives. Here we would look at the first, or the partial of f with respect to x, and we would evaluate that at x equal u naught and u equal u naught, and scaled by x minus x naught, plus the partial of f with respect to u, evaluate that at x equal x naught and u equal u naught, and then we simply take the second partial of f with respect to x, the partial of f with respect to x, then the partial of f with respect to u's. That's just a bunch of higher order terms that we are going to assume, since they get scaled by x minus x naught squared, u minus u naught squared, x minus x naught cubed, u minus u naught cubed. If those are close to each other, those start getting smaller and smaller, those x minus x naughts, or those delta x's and delta u's. For that reason, we are simply going to throw those away. Now, what we are going to do is we are actually going to look at the variation of our system around that nominal operating location, f of x naught u naught. If we subtract that from both sides, and by throwing away those higher order terms, we actually end up with f of x u minus f of x naught u naught approximately equal to the partial of f with respect to x evaluated at its operating location, x minus x naught, plus partial of f with respect to u and that will be our linearization of this nonlinear behavior. And what we're doing is we are now looking at this variation around the nominal operating condition. And if you look at it, these particular pieces right here, when evaluated at the nominal location, just become constants. And now we have some variation around our nominal point equaling a number times delta x plus a number times delta u. And now that delta and x and delta of u give us the behavior that we're interested in. So let's look at that in terms of our original system or our example system. Our example said we had x prime is equal to 2x squared of t plus u of t. First thing we want to do is find a nominal operating point. And one way to find a nominal operating point would be to say, oh, when is that derivative equal to 0? Then I would be at an equilibrium condition. And then I can say, what's my system going to do? How is it going to behave around that nominal operating condition? The nominal point, or a nominal point, that we can try is suppose that we pick x naught equal to 1 and u naught equal to minus 2. What we want to do is see if indeed that gives us a true expression. Does x prime at this location, x not equal to 1 and u not equal to minus 2, equal to the right-hand side at that same location? What is x prime of 0? Well, that's we're defining as f of x naught of t, u naught of t. If we differentiate x naught, what do we get? If I differentiate a constant with respect to time, what do I get? I get 0, don't I? Now, what if I plug in for 2x squared plus u? If I now plug in x not equal to, or let me say x equal x naught, which is 1, and u equal u naught, which is minus 2. Then I have 2 times 1 squared plus minus 2. Or 2 minus 2, which is equal to 0, and so we have verified our nominal operating point. Our nominal operating point does satisfy the nonlinear differential equation. That's what we're after. We now know that x not equal to 1 and u not equal to minus 2 will or does satisfy the governing differential equation. What we will probably do when we talk about this is we may use some notation. Let me just introduce what I'm going to possibly be using. X minus x naught, I may just call that delta x. And u minus u naught, I might just define that to be delta u. Or, if I solve for x, x is now x naught plus delta x, and u is u naught plus delta u. So that now we could look at that another way. We could say, oh, let me find the derivative of x prime. Well, that's now x naught plus delta x prime. That's now x naught prime plus delta x prime. And we are going to let that equal this f of x naught u naught plus partial of f with respect to x delta x plus partial of f with respect to u delta u, where we are evaluating these partials at the operating location. And what we want to do is we want to make sure that this is actually equal to that, and now we have dynamics of the small variation of x around that operating point are equal to these first order relationships in delta x and delta u. Because, whoops, since these two are equal, then we end up with this delta x prime is equal to partial of f with respect to x delta x plus partial of f with respect to u, and this is really an approximation delta u. What if we go back to our example? Our right-hand side was this 2x squared plus u. This equation in red says we need to take the partial derivative of that right-hand side with respect to x and with respect to u, and evaluate at the nominal operating condition. If we take the partial of f with respect to x, what's that going to be? Now we treat everything else as if it was a constant and only look at x as our variable on the right-hand side. What happens when I differentiate the right-hand side with respect to x? 4x. That's not so bad, is it? Now, if I take that result and I evaluate it when x is equal to x naught and u is equal to u naught, because in general I might have both x's and u's present after differentiating that. X naught was 1 and u naught was minus 2. So what does partial of f with respect to x at that nominal operating point become equal to? Just our number 4. And that's now going to be what we introduce, or will be right in here. There's our number. We now have delta x prime is approximately equal to 4 delta x. Now we need to find the partial with respect to u of f. If we now take the partial of f with respect to u, what do we get? That's just 1. Now, here's the really difficult part. Let's evaluate that at that operating point. 1. That was hard, wasn't it? There were no x's and u's left over after differentiating, so that's going to equal 1, whatever x naught and u naught were. Now we have those partials. We can now write our linearized dynamics for that original nonlinear system. Meaning now we have the behavior, the time rate of change of a small variation in x, small variation of x's derivative, delta x dt, is equal to the partial of f with respect to x evaluated at the point, which is just 4, times delta of x plus partial of f with respect to u delta u. If those deltas make you a little nervous, just rewrite it. You could just say, okay, our system behavior is going to be governed by, let me just call z equal to delta x. Now I have z prime is equal to 4 z of t plus, let's say, delta of u, let's just call it v of t. We are now interested in the behavior of this system, which near to that operating point is going to be describing the dynamic behavior of that original nonlinear system. But this system is linear, and we can play with this one more easily than the nonlinear system. That was the whole point. We wanted to approximate this nonlinear system dynamics with linear dynamics, but we're restricting our attention to where this system is located in terms of its operating location. Now I could start asking you all sorts of questions relative to this system. I could say, is the system stable? And now you're going, I don't know, that was a time domain. Well, what are we looking for stability? What do we need to happen for our system to be stable? If we're talking about the S-plane, and I now have sketched the S-plane, what are we typically thinking about when I say, oh, if you now have a system, and I'm concerned about its stability, now you want the poles, or these x's in your x's and O diagram, your pole and zero diagram, you want all of your x's to be in the left half plane. That will give you negative real parts. Yes? So the question was, does that include on the imaginary axis? Anybody want to help answer that question? So you'll hear this many different ways. I hear somebody saying, is that marginally stable? No. I would say if you're on the imaginary axis, that's not a good thing. Because what's going to happen when you kick the system? It's just going to sit there and shake forever and ever because there's no damping. It's on the imaginary axis. Your damping term, e to the something t, is 0. All you have is an oscillator. If you now had poles on the imaginary axis, you would have an oscillator. And if you were ornery and started exciting that system right at that frequency where it wants to oscillate, you're going to go unstable. So I would say you probably want to be, well, you do want to be left of the imaginary axis. But somebody could say, well, that's marginal. Yeah, you hit it, and all it does is sit there and shake. So it's on the verge, but if you excite it at the right frequency, you can make that system go unstable. So you want to stay away from the imaginary axis. If we're looking for stability, we want our poles if you're wanting to text this, you can just say, okay, the poles are in the LHP, in the left half plane. And we know that that means the complex S-plane. So if somebody is looking for stability, they say, oh, are the poles in the left half plane? If we go back to our example, which we've now linearized our nonlinear system, we now have this time domain expression. And if you're not as familiar with the time domain and eigenvalues, then you're going, I don't know, where are the poles? The poles are a transfer function, and that's a frequency domain concept. That's why I said we need to get comfortable going back and forth between the time domain and the S domain or the frequency domain. What if we take that into the frequency domain to find the transfer function? If we had the transfer function, then we could find the poles, and where are the poles in a transfer function? It's the values of S that cause the denominator of your transfer function to vanish. So you set the polynomial in your denominator equal to 0 and you find those roots. All of those roots need to have negative real parts, and that will put them in the left half plane to be stable. Let's then look at this system, or take it into the frequency domain to allow us to find a transfer function. And if we're looking for a transfer function, we don't have to worry about those initial conditions. We're going to neglect the initial conditions for the transfer function. Now, what happens when I Laplace transform a derivative? Neglecting initial conditions. That's simply multiplication by S, and I now have S z of S. What happens when I Laplace transform the right-hand side? Simply have 4z of S, 4z of S plus v of S. Zebra plus violin. 4 zebras plus a violin. Is that system stable? If you have 4 zebras and a violin? Sorry. Let's find out. How do we find the transfer function? That's pretty easy because we already now have just Z's, zebras and violins, Z's and V's. And that's all we need. We need to find the ratio of Z over V to get our transfer function. If we combine the Z terms, now our transfer function, G of S, for the linearized version of the nonlinear dynamics Now, how many poles, what's the order of this system? First, so maybe I need to change my grammar. The pole of G of S is at the value of S where the denominator vanishes. We said S minus 4 equal to 0, and we see that we are at S equal to plus 4. That's not where we wanted it. That's in the right half plane, which this particular system is actually unstable. Meaning, this nonlinear system, when we linearized it, we would probably want to put a controller around it because nominally it's now going to go unstable if we try to excite it around or move it around that operating point. We now need to figure out how do we stabilize that, and that will be later on. If we looked at the impulse response of that system, just to convince yourself that it isn't unstable, the impulse response says, hit that system with an impulse and see what happens. Basically, energize the energy storage elements in that system and see how it relaxes, or what happens when you hit it with an impulse. Then we have this little g of t, which is the inverse Laplace of g of s. And now we have to go back to our Laplace transform table, and what happens when we inverse Laplace 1 over s minus 4? E to the 4t, and that's just going to go unbounded as time gets larger. Meaning we would probably want to, in this case, if this was our system, g of s, we might actually want to measure the output, feed that back, and compare it with maybe a reference signal, send the error between the comparison of where we want that system to move to and where it actually moved to, send that into a controller. Now I have to remember notation. Let's just assume that our controller we're going to call d of s. And hopefully that controller that we design stabilizes the system. Here is our controller. And there was our system. And our goal in this class is to figure out how do we create these capital D of S's. How do we build these to stabilize unstable systems, or shape system behavior that we're maybe not that thrilled about in terms of how it's behaving right now? Questions on linearization? Everybody knows how to do linearization. You're experts. Well, let's bump it up a notch. Let's go to the vector case. Before we were just doing the scalar case, x was just a scalar. What if x was a vector? Then what? Instead of maybe just having x as a voltage, maybe we have voltage, current, position, temperature, pressure. We have a bigger state vector. And we want to linearize the dynamics of a nonlinear system. Well, now wait a minute. Let's not go so fast. Let's do a vector case, but let's not grow that vector quite so tall so fast. Let's look at x being a vector. But let's go in small steps. Suppose that x is just x1, x2 is just two-dimensional. Or we're looking at the second order case for now. And if we understand the second order case, hopefully everything else will fall into place for higher order systems. What do we have? We now have x prime equal to f of xu. That's the same. But now x is tall and thin. F has to be tall and thin to be compatible with x. This simply says that we have x1 prime, x sub 2 prime equaling f sub 1, x1, x2, u, f sub 2, x1, x sub 2, u. And now we have two different right-hand sides that could, one, be nonlinear. They could both have nonlinear terms, but we have to figure out how do we linearize those two right-hand pieces, f sub 1, f sub 2. And if we had a higher order system, what would happen? how would this change? If I had a fourth order system, how would this right-hand side, what would it look like? Just add two more rows, right? We would have an x sub 3 prime equal to f sub 3 of x1, x2, x3, x4, u. And u could be a vector, couldn't it? U could be, no, not y-o-u, but u. We don't want to do matrix, I don't, but we're all vectors, who knows? So now, do you see how this will generalize to a higher order? What does this look like for the second order case? Now we have x sub 0 prime plus delta x prime in general, because x is x naught plus delta x. That's now x, and here's the notation. Let me say x sub 1 nominal, so it's x1 0 prime, x2 nominal prime, plus delta x1 prime, delta x2 prime. I'm just breaking that out into what we know it is going to be. That's now going to be approximately f1 of x1 0, x2 0, u 0, f sub 2 of x1 0, x2 0, u of 0. Plus some partials. What are those partials going to look like? We now have f sub 1 that's a function of x1, x2, and u. And we need to take f1's partial derivatives with respect to x1, x2, and u. And we can put that into a matrix notation. The partial of f1 with respect to x1 and evaluate at the nominal location. That will be scaled by, what will it be scaled by? A delta x1, right? Partial of f1 with respect to x2 will be scaled by delta x sub 2. Now, how do we put that into a matrix? Now we have the partial of f1 with respect to x1, and we have the partial of f1 with respect to x2, and those are going to be scaled by delta x1 and delta x2. And what we have to remember is that we are evaluating those partials, just like we did in the scalar case, at x1 equal to x1 0, x2 equal to x2 0, and u equal to u 0. And that's just the partial of f with respect to the x's. We also need, so this is supposed to be going on to the right-hand side, but I don't think your paper is infinitely wide like mine could be. But I won't do that. I'll just do it below. Now I have the partial of f1 with respect to the input, u, times delta u. And again, this has to be so how do I fill in the bottom row of these two? What's going to be in the bottom row of the matrix that is scaled by our small variation in the state vector, delta x? So now the F2s are going to be involved, aren't they? This is the second row. This is now the partial of f2 with respect to x1, and that gets scaled by delta x1. Partial of f2 with respect to x2 gets scaled by delta x2. And now down here I have partial of f2 with respect to u. Now what we know is that these two terms right here, they're on opposite sides of the equality sign, or that approximation sign, but those are supposed to be equal at the operating condition. Which leaves us then with the following linearized form for a second order system dynamics. We have delta x1 prime, delta x2 prime is approximately equal to partial of f1 with respect to x1, partial of f1 with respect to x2, f2 with respect to x1, f2 with respect to x2, and those partials, or those matrices of partials, now have to be evaluated at the nominal operating point or condition. Let's see if you can do a second order. Now we have x double prime is equal to, let's just say, g of x, x prime, and u. Suppose somebody gives you that the second derivative of x is equal to 4x plus 6x, x prime, minus x prime squared, plus u, x prime, plus 5u. First thing you want to ask is that linear or nonlinear? Do I even need to linearize it? If it's a linear equation, I can just put it into matrix form or just deal with it the way it is. If I wanted to find a transfer function, I could Laplace transform a linear equation and go. If it's not linear, I can't Laplace transform. Is this system linear or nonlinear? It's nonlinear all over the place, isn't it? We have an x times x prime. That's a nonlinear. That would make the whole thing nonlinear. We have an x prime squared. That's nonlinear. We have a u times x prime. That's nonlinear. It's really nonlinear. But this right-hand side is what we could say is our g of x, x prime, and u. Now what we want to do is create this in a structure that will be consistent with what we just developed, which had F1 and F2s in it. And now all I see is one G. Where's the G1 and the G2? Doggone it. How do we convert this to a compatible form that we had before, which was, let's say, an x1 prime and an x2 prime? We need to find something when primed yields x double prime. Or if you wanted to think about it, an acceleration if we were thinking about position, velocity, and acceleration. A velocity, when differentiated, would give us an acceleration. So we need a position and a velocity. Our states, then, and what we will do is I'll give you this to work on for tonight. If you let x or z1 equal x and z sub 2 equal to x prime, I claim that you can now put that into a z1 prime equal to an f1, a z2 prime equal to f2, and you can linearize that like we've talked about in the earlier part of today's lecture. I'll leave you with that to work on or to chew on, depending on how you want to proceed.